All right, so let's look at the solution to Terzaghi's one-dimensional consolidation equation. We're going to use separation of variables here to solve this partial differential equation. So we'll assume that the pore pressure as a function of z and t can be represented by functions that are only a function of depth, f of z, or a function of time, phi of t. Now substituting the separated expression back into the differential equation, we arrive at the expression shown here. Can do a little bit of algebra to simplify this out and separate the z's on the left side and the t's on the right side. I'm going to move the c sub v over to the right side because it'll be a little easier to work with it over there later on. Now the only way that these two expressions can be equal to each other is if they're both equal to the same constant. Okay, changing time doesn't change the expression on the left, changing depth doesn't change the expression on the right. So let's assume that the constant they're equal to is minus a squared. The reason for that will become apparent when we solve the differential equation for z. So now we have f double prime of z over f of z is equal to minus a squared, or f double prime of z is equal to minus a squared f of z. Prime, by the way, just denotes differentiation with respect to the variable. Similarly, we have phi prime of t is equal to minus a squared times cv times phi of t. Now we've reduced the partial differential equation into two linear homogeneous differential equations, ordinary differential equations. And so these are fairly straightforward and easy to solve, so let's move to that next. Let's start with the depth differential equation. F prime of z is equal to minus a squared f of z. The solution to this expression is simply a combination of harmonic functions. F of z is equal to c1 cosine of az plus c2 times sine of az. Now let's go to the phi prime of t expression, minus a squared c sub v phi of t. The solution to this differential equation is that phi of t is equal to the exponential, or c3 times the exponential of minus a squared cv times t. So now we can write out our expression for u of z comma t, having solved for these ordinary differential equations. c1 cosine az plus c2 sine az times c3 e to the minus a squared cv times t. Now we can lump these constants together. There's no reason to retain separate expressions for c1, c2, and c3. So let's let c4 equal the product c1, c3, and c5 equal the product c2, c3. Making our substitutions, we now have only two constants to solve for in this differential equation. And we end up with the expression that's shown here. Now let's talk about boundary conditions. I'm going to solve this problem for a double drained layer. So that means that the pore pressure at the top of the layer is 0 at all times, and the pore pressure at the bottom is 0 at all times. We're also going to assume that the initial pore pressure is constant throughout the layer, so that means that u at all depths at time 0 is equal to ui. Now if we solve the first BC, we'll say that 0 is equal to that expression for pore pressure at depth equals 0, so I'm substituting in here the zeros on the cosine and sine terms. The only way that that expression is true is if C4 is equal to 0. Okay, now we go to the second boundary condition, and we have 0 is equal to this expression now where we're substituting the depth at the bottom of the layer. So the AZ term would be 2AH, and we have e to the minus a squared CVT. Now I've taken out the C4 cosine term because C4 is 0. Based on this expression, we can solve for A. A must be equal to n pi over 2h, where n is any integer. You'll find that plugging that in for A will always result in the second boundary condition expression being 0. So we now have an expression for pore pressure that's become a bit simplified. We have C5 times the sine, and now I'm going to substitute in for that A term, so it's n pi z over 2h, e to the minus n squared pi squared over 4h squared times cv times t. Now we're going to do a simplification here. N can be any integer, and c5 is an arbitrary constant. Therefore, we can take the solution and represent it as an infinite series. So I'm going to do that for reasons that will become apparent shortly, but we can write the expression now. U of zt is equal to the infinite series b sub n sine of n pi z over 2h e to the minus n squared pi squared over 4h squared cv times t. And now we can look at our third boundary condition, which is that the initial pore pressure is equal to ui, and that's at all z's at time equals 0. So we can just take the first part of that expression. Note that the exponential of 0 is equal to 1. So the third BC gives us this expression. Now what I'm going to do is invoke a couple of definitions to help us interpret this expression. The first one is integral from 0 to pi sine mx sine nx dx is equal to 0. Second one is sine squared nx dx equals 0, where m and n are integers that are not equal to each other. You can find these in any table of definite integrals. So what we'll do now is take our expression, multiply by the sine m pi z over 2h, and integrate from 0 to 2h on both sides. Here I'm writing out the expression on the other side as well. Okay, and what we find is that that expression on the right is going to be equal to 0 anytime that n and m are unequal, based on that expression we just looked at on the previous page. So we can simplify that by just substituting in the n expressions. Therefore, we get the integral from 0 to 2h ui sine of m pi z over 2h dz is equal to, now we can remove the summation because it's 0 for all m unequal to n. Therefore, there's only one term in the series for which the expression is non-zero, and that's the sine squared n pi z 2h dz equation. All right, so we've been able to use those definitions to simplify the expression. The other expression indicates that the integral on the right is just equal to bn times h. So now we have our expression for the bn terms. Those are all of the constants in that infinite series. 1 over h, the integral from 0 to 2h ui sine n pi z over 2h dz. And I've made a substitution for m and n here. They're both just constants, so that's perfectly fine. Substituting that into our expression now for pore pressure, we get an infinite sum of this expression shown right here. And now we can simplify that definite integral, the integral from 0 to 2h ui sine n pi z over 2h dz. And if you simplify that definite integral, you get a slightly more compact expression that I'm writing here. Now I'd like to point out that we can make some things dimensionless here. So let's take z over h and call that capital Z. Let's take CVT over h squared and call that capital T, where capital Z is a dimensionless depth and capital T is a dimensionless time factor. We now have still the initial pore pressure, but we can also make that dimensionless by defining this degree of consolidation, 1 minus u over ui. So the degree of consolidation is 0 at time equals 0, and it goes to infinity, or it goes to 1 as time goes to infinity as consolidation finishes. So making our substitutions now, we have an expression for the dimensionless degree of consolidation as a function of dimensionless depth and dimensionless time factor. This dimensionless equation can be applied to layers of any thickness and with any initial pore pressure condition for any double drain condition, so it's very general.